Hi everyone, in this video I'm going to show how to derive Fourier series expansion using complex Fourier series. Alright, first we need to identify a period for the given signal. Alright, so we have two options here. Okay, the first option, okay, is to select negative 5 over 2 to negative 1 over 2. The next option is to select the signal from negative 1 over 2 to positive 3 over 2. So you may select either one of the cycle. Alright, so for this example, as I said, I'm gonna select only one cycle. Alright, and the period that I'm actually selecting is from 3 over 2 to negative 1 over 2. And for this period, the function is behaving or producing a value which is positive 1 and negative 1. Alright, so I'm going to list that here as the function which is xt. Alright, for the range of time that we have selected, it's producing 1 and negative 1. Okay, so this one is being produced for the time duration of negative 1 over 2 to positive 1 over 2. So I can just put it here, right? So positive 1 over 2 and negative 1 over 2. Okay, alright. So the next value that I have selected is negative 1, which is from positive 1 over 2 to 3 over 2. So we can write that here. Okay, is in between of this. Right. Now we have selected the period and the behavior of the function for the period selected, and we also need to determine the fundamental period. Means here we have selected the range. So what is this range is all about? Okay, so if you notice, the function this period is actually from negative 1 over 2 to over here is half, right? So from here to this point is 3 over 2. So basically, if you want to find the fundamental period, okay, so you just take half, which is from this point to here, plus the value from this point to here until it completes one cycle, which is 3 over 2. So this one going to produce 4 over 2, which is equivalent to 2. Alright, so now we have determined the fundamental period, and we also determine the behavior of the function. Alright, so next you may write the general equation for the complex Fourier series expansion, which is from the previous videos. Okay, you can know, right? So the Fourier series expansion for the complex Fourier series, okay, is shown like this. Okay, your n is from negative infinity to positive infinity, meaning any value from this range. Okay, you have xn, then which is this xn is being multiplied with the exponent with j to pi n over t naught. This is t. Okay, so in order for you to solve this, you need to find your xn. Okay, so this is where we need to do the integration. Okay, so the xn by formula is given as 1 over t naught from alpha, okay, from any value to any value plus the fundamental period. Okay, it not necessarily always have to be start from 0, right? So that's why we are selecting, we are putting the alpha, right? Okay, next we substitute, we are representing the signal behavior for the period that we have selected. Okay, and multiply with exponent okay, 2 pi n t naught t, and this integration is being done with respect to dt. Alright, so we're going to use this formula, alright, to find xn, and we're going to substitute the xn in the Fourier series expansion that I've just written here. Okay, so let's start. Alright, so if you look at this signal, okay, it is behaving or producing two values for the period that we have selected, which is for the period of 2. Okay, so if we want to substitute this range, okay, we can't do it straight, okay, we have to split into 2. Okay, I'll show you here. Okay, basically I wanted to do this integration. Okay, if I want to substitute the value, okay, t naught, we know it is 2. The range that we have selected, okay, it's actually from negative 1 over 2 to positive 3 over 2. Okay, this is a range, but for this range we have two different xt, okay, which is positive 1 and negative 1. So that's why we have to refer to this one. Okay, so for this particular range, xt going to produce 1, whereas for this particular range is going to produce negative 1. Okay, so I'm going to split this integration into 2. Okay, so let's erase this off. Okay, negative 1 over 2 to 1 over 2. Okay, in this range your xt, the xt is positive 1. Okay, so we should put a bracket here because we're going to have two different integration, right? So we put a bracket here. Okay, this is for this one. Okay, and we may copy this, but make sure we substitute, okay, the value t naught is 2. 2 and 2 we can actually cancel off. So after cancel off, we have left with j, pi, and t. So this is what we have, and this integration is with respect to dt. All right. Next, okay, next I'm gonna have another set of integration, which is from positive 1 over 2 to 3 over 2. Okay, for this we're gonna have negative 1. Okay, with reference to the previous set of data that we actually written. Alright, so here is gonna be similar and t, and this is dt. Okay, so so this is what we're gonna do. Alright, so we're gonna integrate this. Okay, so if we integrate, okay, let's do that. So I'm going to use different colors to show you the differences. Different color for the bracket I'm referring to. Okay, so I'm going to use maybe this color. Right. So this is to represent this whatever happening in this integration. Right. So if you differentiate this, you're gonna get if you differentiate this, you're gonna get negative j pi n. This is what you're getting. Okay. Alright, so your exponent will remain because it's the integration. Okay, and we can close bracket, and we can have the value over here. Okay, right, now we can have different color for this bracket. Okay, then we differentiate, we integrate this similar to what we have done here. We have to differentiate this. Okay, 1 over negative j pi n, here same, negative j pi n. Okay, so it's going to be t, and we can actually close this bracket, right, and this is for 3 over 2 to 1 over 2. Okay, alright, so there's one important point here. Okay, this negative, I can actually bring it in front here to make this as negative. So I'm going to change this, okay, to negative. Okay, so I've brought the negative in front, so it's become negative now. Alright, so now we close this bracket. Okay, next is to substitute the values. Okay, so now we have already substituted the value in, right, as you can see. Alright, so I've put in the positive 1 over 2 here, the negative 1 over 2 here, positive 3 over 2, and positive 1 over 2. Right, so these are the values that we supposed to put in. Alright, so I've already done that. And here, okay, what I did is I have taken out the common factor across these two, okay, and kept it outside, okay, which is negative j pi n, so I kept it outside. Alright, so this negative and negative will become positive. Okay, so you don't find a negative symbol here, and over here I just maintain this negative because we're going to use it later, right, for other conversion purposes. Alright, so now we have this, okay, exponent to the power negative j pi n 3 over 2, and negative exponent to the power negative j pi n over 2. Right, so this is what we have. Alright, next we're gonna expand this. Alright, expand this so that we will get a common factor, and we can do some simplification. Alright, for this, that's what I'm going to show you now. Okay, over here is exactly same. Alright, so I just copied here. Alright, this is exactly same, no changes over until here. Alright, no changes. You look at this colored one. Alright, this is negative 3 over 2, which we can write as negative half plus negative 1. Similarly, here we want to produce negative 1 over 2. Hence, we can take negative 1 plus half, which will eventually produce negative 1 over 2. Okay, the reason we are doing this so that we can actually expand this plus symbol. Okay, if whenever you have exponent to the power, okay, where you have a plus symbol, which you can actually write as a product. Okay, and you look at this one. Right, so you have this common. Right, this is common for both. Hence, I can actually take that out. Alright, so if I take out, it will look like this. Okay, so we have taken out, basically I've taken out the common one, which is exponent to the power negative j pi n. Right, hence this is what left. Okay, this is what we have left. Right, so now we look at this. Okay, we get almost similar pattern. Right, we got this almost similar. Alright, so next what we're going to do is we're going to bring this 2j in, okay, which is 1 over 2j in basically. So we're going to get this one. Alright, similar over here. Alright, so if you notice, alright, if you notice, what am I going to do is actually I'm going to convert this into a sine form. This thing can be rewrite as sine pi n over 2. Okay, here also same, sine pi n over 2. Alright, so the next thing, okay, that you have to take note, okay, is 1 over pi n. Okay, so after this thing repeated twice, hence we can actually do the factorization. Okay, so we take it out actually. We taken out, okay, and this is what is left. Alright, so you can take out the common one over here, sine, okay, which will only left, okay, with 1 minus exponent negative g pi n. This is what we have left. Alright, so now we're going to look at how to simplify this further. Right, so for that I'm going to use Euler's rule. Okay, right, so it defines that, okay, exponent to complex value is actually equals to cos x plus j sine x. Alright, so if I let my x as, let's say, negative x, so I'm going to substitute that into this. Okay, so I'm getting sine negative x. Okay, note that cos negative x is equals to cos x. Sine negative x is equals to negative sine. Okay, so we're gonna substitute that into here, which gonna produce, okay, alright, so this is what we're gonna get. Alright, similarly for our case, okay, this is what we have, okay, and pi, right, cos whatsoever that I have here, okay, I need to substitute here, okay, I put it as cos n pi, right, cos n pi. Alright, here we're going to have negative as what we are seeing here, sine. Okay, so this is what we are getting. Alright, and another thing that we have to take note that sine for any pi, okay, for any pi will be 0. Okay, for any value of pi it will take 0. So n is just like 1 pi, 2 pi, 3 pi will be 0. So hence this entire thing I can see as 0. Right, so I can say this, okay, is as cos n pi. Right, so we're going to take this idea and substitute into our xn value that we just obtained. Okay, so we still gonna get Okay, this one still remain. We know we are not changing it, and pi over 2. Okay, then this thing we can change it as cos. Okay, pi. Okay, we maintain the same method. Okay, let's just put it as cos n pi. So this is what we are getting. Write that here. Okay, and the Fourier series expansion for xt. Okay, so you're gonna get, okay, this is negative infinity, and let it be positive infinity, negative infinity. Okay, I just can write like this, because this is your xn, right? Just copy. Okay, 1 minus cos n pi. So we're gonna get something. Okay, okay, so you may explore this further, right? I think for now this is good enough. Okay, if you solve, so now you got the solution in the form of exponent Fourier series, right? So hope this video helps you. Alright guys, thank you.